Good morning. November 18th, we are recording this class. This class is on gearing and gearing applications. And thanks for attending. Week before Thanksgiving. I'm assuming you can see my screen. Should say simple conveyor application. And so let's go to the top. We are talking about gearboxes and gear types, and we will end with two applications, a conveyance application that can also be an indexing application, and an azimuth elevation application. And as I said during the introduction before starting the recording, these are widely applicable to a number of applications using the same calculation techniques and the same principles. So I want you to just forget about gearing, which may sound odd, and when you talk about these kind of applications, but focus your attention in your mind on the target shaft. Let's say that you're responsible for amp, motor, maybe with a brake, and a gearbox, and that the gearbox at that point drives some mechanical drivetrain on its output. Maybe it's a belt going to some rollers on a conveyor. Maybe it's a pinion on a big ring gear driving a turntable. But I want you to focus on the target shaft that you're responsible for, because our job, regardless of what is upstream of that shaft, is to make that shaft go at the speed and torque that the customer wants. And maybe it's continuous duty speed and torque, and maybe it's variant over time, making it a little bit more complicated. But that target shaft performance is your focus. Now, we're going to require a lot of data to size everything upstream. And that data should be applicable to the target shaft. So some basics here, and these formulas are published in this presentation for your convenience. Basically, torque, very important to size a gearbox. And continuous duty torque versus peak torque. Peak torque typically occurs during accelerations and decelerations. An indexing move, going from point A to point B as fast as possible, is nothing but an accel and decel move. Because you're going from point A to point B as fast as possible, you're accelerating the entire time until you have to decelerate to stop on the designated point. There's no time to run at a constant speed. But there are a lot of applications like conveyors where you accel, you run at a continuous speed, and then you decel at the end of the cycle. So those, note, are force times radius to get the torque you want. And for example, you are driving a belt, and the belt is driven by a sprocket that's mounted on the output shaft of your gearbox. That sprocket has a radius, and the belt has a required tension to pull the load that you're trying to move with your gearbox. Therefore, you have the torque number that you need to size your gearbox. That would be the output torque of the gearbox. The torque to accelerate the load is going to require the inertia of the system. This is often very difficult to obtain in the conversation with the end user that you're dealing with, but it must be required to do the numbers. And by the way, we focus on the numbers here. We don't take guesses. We try to quantify everything to get an accurate gearbox that's not too expensive. So a vertical lift, that's a very simple calculation because you have a radius on the drum, which is the circle here. The red line is the radius. Then you have a weight. And going back to this formula, force times radius, well, the weight is the force, and the radius is the radius. What's interesting about this is that with a simple use of trigonometry, and you don't have to know trigonometry, all you have to do is know how to look up a trigonometric table, you can now calculate force, torque along an incline. And these are the forces that are associated with an incline. The hoist is a special case where theta, the angle, is actually 90 degrees. Not inclined, but vertical. And of course, the friction vectors that would be used on an incline are zero because you have no friction other than windage, which is completely insignificant in lifting the load. So on an incline, we have more things to deal with, but the basic radius and force vector are still in play. We have to add other things. So whereas we have an angle of theta of 90 degrees in a vertical lift, and let's just call this 45 for the sake of our discussion. The sine of, is it the sine? I haven't had my second cup of coffee yet. Yeah, the sine of theta is, in the vertical, is 1 when it's 90 degrees. And it declines all the way to 0 when you're pulling the load horizontally. So you can see how convenient the sine of theta is to varying degrees of inclination all the way up to vertical in this particular application. So you need to know your angle, and then you need to go to the table, Google it, the sine of an angle, and that'll get you a table. And at 45 degrees, you'll have a value that's somewhere between 0 and 1. At 30 degrees, you'll have a lesser value, but still between 0 and 1. It becomes the multiplier on all of the other calculations that are associated with this particular application calculation. There's a very nice explanation of this in detail in this link. So, by the way, let's go back to that because I think you can see this. Let me scale it up a little bit. This is not complicated, although it might appear so initially. Here is your weight of this object. This is the force factored by theta that goes into your calculation for torque. This is your friction coefficients. So you can obtain this data from the customer or through your own calculations if you're the designer. Obviously, if you're rolling up this incline on ball bearings, your friction is going to be published by the bearing manufacturer based on the weight on the bearings. If you're sliding up that, well, it's the surface area of whatever you're dragging up versus the type of surface versus any lubrication you may have. These are all mechanical engineering items that are very simple and easy to get. So again, we're not talking about a significant amount of rocket science here. We're just talking about getting the data. And when we want to do the application right, getting the data, I can't emphasize this enough, is important to get to a hard number that allows you to size the equipment properly. So let's look at a typical velocity profile. Let's scale this back down too. In a velocity profile where we make a move, we have an acceleration, we have a run at speed, and we have a deceleration. As I said, in the indexing application where we're going from point A to point B as fast as possible, TC is 0. And TA and TD don't necessarily have to be the same. When you accelerate, you're going against a lot of factors, which will going to require more torque, which may limit the acceleration rate of your system. When you go down, some of those factors act to help you decelerate, such as the coefficient of friction, which means you could potentially decelerate faster. In the up direction on a lift, gravity is working against you. Again, limiting your ability to accelerate to speed in the fastest time possible, but gravity works with you on the decel. Now, if we superimpose some values on this, the green line is actually going to be, I don't know what I put the green line in there for, to be honest with you. The red line is your acceleration currents. And in accelerating, and this red line isn't perfect because it should be out here. I just kind of scribbled it in. But when you go acceleration, your amperage, and therefore the torque required to get to speed, is going to cause a peak. And therefore that affects the peak values allowed on the components you are selecting. So in this particular case, while accel and decel have high values of torque and therefore power, therefore strain on your system, running at speed is, as you can see, somewhat easier on the system. So in this particular case, the point being, you will need to know the peak capability of your system and the continuous duty capability of your system. And in some cases, the peak is going to limit the application, and in some cases, the continuous duty is going to limit the application. When I say limit, it determines the sizing of the components. A very slow accel and a long run, say 8 hours on a conveyor, the continuous duty is going to be the factor required. And the fact is that you can accel on those applications usually pretty slowly, and therefore not have any requirement to get to speed as fast as possible, thus straining the system and constraining the sizing applications of the components you're using. It will be this section here of the application which will determine the sizing of the components. However, if you have an application like a shuttle where you're taking a whole bunch of molten iron and out of the melter, and you're basically moving it 100 feet over to pour it into the place where you're making ingots, the accel and the decel there may be your limiting factor on selecting the components. So we're going to be focusing on these numbers here to make the selection. Every component that you have has intermittent and continuous duty performance, typically in a chart such as this. Now, this happens to be a motor performance chart. And you can see that once you reach the base speed of the motor, you start to get declining torque in the continuous duty region. Here is the limited duty region. Maybe this here, this value here is very close to continuous, but this value here may be 3 seconds. And that means that that you can use this torque only for a very short period of time, for example, a sharp acceleration. Note that the rate of the peak capability of your motor drops precipitously compared to the continuous duty rate of decline above the rated speed of the motor. This is 1 over n, where n is the ratio of the velocity to the base velocity or rated velocity. This is 1 over n squared. So when you go above the rated speed of a motor, your peak capability drops much faster than your continuous capability. Again, something to keep in mind. At that point, the motor may become the limiting factor in your drivetrain. Again, thinking about an amp, a motor, a gearbox. This constraint, especially when you want to run above the base speed of the motor, may become the limiting factor in your capability of the system overall. Now, this is a chart that helps us to get to the numbers. And it often comes from the software associated with the servo amplifier. And in some cases, you can do some predictive charting if that servo amplifier has that capability in its associated software. So make use of this as you go ahead and try to size things. Here is your position. We start off at point 0 and we move to this point here. This happens to be your velocity, and as I said before, in an indexing application, you're going to accelerate as fast as you can, and then you're going to decelerate as fast as you can. In this particular case, the accel and decel are the same, so there must not be a lot of friction component here. Here is your acceleration value and your deceleration value. Note that they are either side of 0. Going back up here, this line is torque. Sorry, I forgot about that. This line is torque. Note the torque is constant. For a constant acceleration and a constant deceleration, that's what's shown here, because the rate of change in velocity is constant, and the rate of change of velocity is acceleration. By the way, those of you familiar with calculus, this is your position. The rate of change of position is velocity, position over time. And the rate of change of velocity over time is acceleration. That's the second derivative. Position is P. This is the rate of change of P. This is the rate of change of P squared, for those of you familiar with calculus. Very integrally linked together. Now, the principle of ratios in gearing and the multiplication of torque and the associated reduction of velocity. You need to be aware of that. Because every time you have a mechanical advantage, you're going to be going faster on this shaft than you are on this shaft, obviously. But the mechanical advantage of the radius here versus the radius here means you're going to have the ability to produce more torque here, even though at lesser speeds. So in a gearbox, you may have 1 ratio reduction, we call it single reduction, 2 ratios of reduction, this is double reduction, and this would be triple reduction. And then you have your output shaft here, which is your target shaft. This is a triple reduction gearbox. The ratio of the total is the ratio of all 3 multiplied together. Now, again, reduces RPM, increases torque, and gearing typically will reduce the cost of achieving the desired performance on the target shaft. It actually has to, otherwise why would you use it? And in most cases, when your motor is, say, 3,000 RPM and your output speed is going to be 300 RPM, you're going to use a 10-to-1 gearbox in most cases. We'll talk about some of the application requirements in a minute, but that is going to be your most effective cost factor in achieving the application. If you were going to use that 3,000 RPM motor and direct drive the load at 300 RPM, then the motor without gearing, direct driving the load, would actually have to be 10 times the power required in order to give you the torque needed at 1/10 of speed. And that would be an extremely expensive motor and amplifier. Putting a gearbox in play with a 10-to-1 reduction ratio allows you to use 1/10 of the motor and 1/10 of the amplifier. So the economics kind of work that way. Direct drive is used sometimes. It's expensive, but it gets you some advantages. Let's talk about that. So gearing adds a nonlinearity to torque and velocity control. If the motor is going a certain speed and the gear geometry is such that it distorts that a little bit, in some applications such as scanning, where the output and in turntables for CNC, for example, you want that output speed to be directly related to the input speed. And gearing can distort that depending on the geometry of the gearing. Gearing adds backlash because the gears don't mesh together perfectly. The gearing has efficiency factors. You got to pay a price to use gearboxes. Sometimes it's a 95% efficiency, and some worm gears can be as little as 60% efficiency. On some of these slewing drives that are used on large turntables, to get the cost down, they don't use high-grade materials. They use typically cast iron and things like that. Some of those efficiencies are 20, 30%. You think about you know what a JLG lift is, one of these construction cherry picker type things. It's got a rotating application on it to rotate the housing around to manipulate the basket that the man is in. And that is a slewing drive. That has a super low efficiency on it, but it economically makes sense in that application because that doesn't move very much. Plus, you got a big old diesel engine driving it. So, you know, in that case, the power is not, the waste of power across the gearbox is not a factor. Now, gearing reduces the MTBF of the system because it inherently adds parts. Plus, it's a mechanical on mechanical motion, and gearing requires maintenance. So these are some of the factors you've got to consider when you add gearboxes. We're going to talk about the different types of gearing in a second. The maximum ratio per stage is important to know. So put this in your mind, because in some cases where you have a high reduction ratio, a worm gear can be very advantageous. Because let's say the application is 60-to-1. The worm can do it in one stage. A planetary has to do 2 stages. 8 times 8 is 60. A spiral bevel gear or a helical spur is going to have to use 3 stages. That drives the cost up. Belt and chain drives. Why doesn't everybody just use a belt and chain drive and not use gearing? Because belt and chain drives are pretty cheap. They're also very efficient. You know, they're well above 90%, especially with some of the new chain technology coming out. 6-to-1 is the limitation on that. Why? Because your driving sprocket becomes too small when you go beyond 6-to-1 to effectively handle the torque required. Another thing to note is the efficiency of your gearbox. This is a big factor because if you use a worm gear in the same application, or you're comparing it against, say, a helical, and you're at above 90% on the helical, the worm gear is going to cause you to have to use a much larger servo motor and servo amplifier, or induction motor and variable frequency drive, as the case may be. That often doubling the cost of those. Another factor to consider. Worm efficiency is not linear. So while most of these are linear throughout the speed range, and therefore linear during acceleration and deceleration. Worm gearing, you need to know this because this can catch you. This can cause you problems if you don't factor it in. Worm gearing is not linear in efficiency. Its efficiency drops as the velocity drops. So you may be 90% on your worm gear at 2000 RPM input on the motor, but as you're varying the speed down, the efficiency changes. So if your application's operating mostly at 1000 RPM, you better figure out what the efficiency of that worm gear is at 1000. Plus, these things are hard to start. They require a lot more peak torque. When we look at the gearing types in a second, you'll see there's a lot more friction on a worm gear because of the greater degree of metal-to-metal contact. That's a good thing because worm gears, you can beat the snot out of them. They take 500% shock loads. But starting them, the efficiency can be as low as 20%. If you don't account for that, and all you've done is accounted for your efficiencies and torques, etc., at your running speed in your application, you'll go to turn the thing on and the thing's just going to go, and the amp is going to overcurrent trip. And then, you're not going to be able to get to speed because you didn't account for the starting efficiencies. Double enveloping worm gears, much better efficiencies than standard worm gears. It's one of the reasons that Cone Drive, which is a company that we represent, so full disclosure, is so successful in doing these applications where standard worm gears cannot play, because the efficiency of the double enveloping worm, as we'll see in a second, is much better. The sliding friction as you start is spread out over 4 to 8 teeth of contact instead of just one. And that makes all the difference in the world in the efficiency of double enveloping worm versus single enveloping worm. So those are, in essence, in my mind, two different types of gearing. And the double enveloping worm can be used in a much broader range of applications, and economically is more viable than using single point contact worm gears. And with the advent of 5-axis CNC, double enveloping worm geometries are no longer 3-4 times as expensive to manufacture as single tooth contact worm gears. Now, this is too much detail. It's all about how we design the tooth interfaces on this particular kind of gearing. This happens to be a spur gear that's pictured. This kind of chart exists for every type of gear geometry we talk about. These are the different types of gear geometries that we use in our world. Just actually, not all of them. Now, I'll leave you to study these. There's the worm gear. We did not represent the double enveloping worm. This is the double enveloping worm. The difference is that this worm is beveled here. So it kind of wraps around the worm gear. This is called the worm. This is called the worm gear. This is a single enveloping worm where it's a straight cylinder. When a line contacts the surface or circumference of a circle, it's called a tangent, and it, by definition, contacts in one point, therefore one tooth. If you bevel it, you get 4 to 8 teeth of contact, depending on the ratio. Thus the advantage of double enveloping worm gearing. More pictures on, this is a straight, this is a helical, this is less noisy, and it's actually more contact surface. This type of gearing is more expensive and superior in performance to this type of gearing. This is nothing more than a double helical. And we'll talk about this in a second. This is epicycloidal. Very unique type of gearing. All right. More on the double enveloping worm. This is a hypoid. Typically, you're going to see this in high efficiency right angle gearboxes that compete with worms. Again, it's a part of your palette. You don't have the shock loading of a worm gear. These are more expensive than a worm gear. They're more efficient. They're also a little bit noisier than a worm gear. One of the other advantages of worm gearing, by the way, is it's very quiet. Here you have all these gears with the space between the teeth, and they kind of rattle along. Now, this center distance principle is very important in sizing worm gears. The larger the center distance, the larger the capacity of the gearbox. So the bigger this gear gets in terms of diameter here, more capacity, obviously, that it can handle. Here are some gearboxes assembled. These are right angle versus inline, which we'll look at in a second. There's the gearbox gearing, and that's how it manifests itself in terms of the total gearbox. Here's your coupling and your motor input. This is your output shaft. This, by the way, is a 1-to-1. This obviously is a reduction ratio of greater than 1-to-1. Here we have torque multiplication, velocity reduction. Here, going through this gear set, we turn the 90, but the speed stays the same, the torque stays the same, other than the decrease due to the efficiency of the gear set itself. Often these are called miter boxes. This is another look, but this is a double reduction gearbox. It's a combination. You can combine the geometries together to create what you want. Here we have a spiral bevel, and here we have a straight tooth pinion and driven gear. Often cases in this set here, the second set, called the second reduction, is going to be helical as opposed to straight tooth. Now, this first reduction runs obviously at motor speed here, and then this shaft is reduced. This shaft drives this shaft through the second set of gearing, further multiplying the torque and reducing the velocity. Now we get into inline or concentric shaft. Concentric shaft means that the output shaft is on the same axis as the input motor shaft. Inline gearing that is not concentric is called parallel shaft. And you have a different degree of form factors here. Which is the input and which is the output on this one? Well, it's pretty obvious based on the diameter of the shafts. This is the input shaft, less torque, therefore less meat required on the shaft, higher speed. Get to the output torque here. This must be a very high reduction box because look at the amount of diameter increase on the output shaft to handle the torque without shearing off the shaft. You have hollow shafts and solid shafts. That's all different geometries associated with gearing. A very interesting type of gearing is called planetary gearing, where it's one of the inlines, okay? Input shaft, output shaft, input shaft, output shaft, but the inside is always very interesting because you drive this gear here, which drives these gears here simultaneously, obviously. Sun gear, planet gear, this is called planetary gearing. This typically is fixed so that when you drive this gear and thus drive these gears in the opposite direction, this carriage rotates. This is fixed and often the inside of the housing of the gearbox itself. This becomes your output. Now, again, another look at planetary gearing. But how do we make this input shaft into an output shaft? Well, it's a piece of mechanical bracketry that rides on the planet gears and turns the output shaft. So this input shaft turns. Obviously, in this picture, it's on the other side. The output shaft on this side is driven by this carriage plate that's attached to the 4 planetary gears. By the way, this is a very common type of gearing in your transmissions of your automobiles. Keep this geometry in mind, because here we have tooth contact, right? And there's associated backlash. There's also less surface area of contact than if instead of using teeth, we used lobes. So teeth, lobes. This is zero backlash gearing in most cases. And it's extremely stiff. I'll define stiff in a moment. And it can transmit a lot of torque because of the extra surface area involved. When you put a lot of torque, you're basically squeezing these balls in between, these can also be cylinders, in between two surfaces with a greater degree of surface area than the point contact of teeth. So more torque, less torque. In addition, there's always contact here. Thus the zero backlash. Here, these teeth have gaps in them. And when you reverse the direction, those teeth move across the gaps. That's called backlash. That's a zero motion point in the gearbox output. It can cause a lot of problems because the motor is moving, your encoder is moving on the motor, and there's no movement on the output of the gearbox because you're going through the tooth gap. It causes a lot of issues, which we'll refer to in a moment. Now, harmonic gearing is a whole different story. And this is somewhat the same principle as cycloidal gearing, but it basically uses this piece here and distorts it the entire time the gearbox is running. It's called strain wave gearing. Harmonic gearing is because of the dominant player in the market. It's called harmonic drive. It's kind of like Kleenex. But it's officially called strain wave gearing. This wave generator here, this is not a circle. This is an ellipse that distorts this and causes these teeth to walk around the inside diameter teeth of this ring in the opposite direction of this, and with high reduction ratios. We'll show a video on that in a second. So, the two types of gearing that are very important in precision applications are cycloidal and harmonic. Also planetary. Planetary is less expensive. It's more used because a lot of applications don't require zero backlash. And these are more expensive, but they achieve the purpose and they're very reliable zero backlash gearboxes. Let's talk about stiffness. The stiffest gearbox is this gearbox here. Just, stiffness is if I put a force on this output shaft. Let's say I put a big lever arm here and I crank on it in one direction. How much? Let me back up. I'm going to put a brake on here, okay, to hold motion, to have zero motion in the system. I needed to say that first. Then I'm going to put a huge lever arm on this output shaft, and I'm going to crank on it and put torque on this output shaft. At zero velocity, I'm going to measure the deflection of the input shaft. If it's zero, it's super stiff. The deflection in arc seconds of the input shaft, of the ability to, let me back that up again. The deflection on the output with this torque arm with the input shaft held fixed with the brake is your deflection and your measurement of your stiffness. Why is this important? A very good application of this would be robotics, where you move to a certain point and your end effector, whatever is at the end of the arm of the robot, needs to do something. Well, if that's a machining operation, or if that's moving or it's getting a force put on it, there's an external force from the load going to try to turn this shaft, and you don't want that shaft to turn. The stiffness of the system will determine how much it deflects under that external load. It's very important in satellites. When you do a rotation and an elevation axis on an 18-meter dish satellite, and that 18-meter dish is tracking some, or an antenna is tracking some satellite, miles in the sky. Therefore, any deflection is going to cause an error at the destination point, and you're going to lose contact with the satellite. Well, satellites with 18-meter dishes, unless they're under a radome, which is a big dome that prevents wind from affecting the dish, and the big ones typically are not, the wind's going to affect them and try to move them. That's that external force that I'm talking about on this output shaft. That'll cause deflection of the whole dish, and the dish will get off target. So that type of stiffness is very important in precision applications. Now, away. Inline gearing parallel shaft. This is a big industrial box. Look at all the backlash because of these types of teeth here. This is not a precision gearbox. This is typically used in giant industrial applications. It's efficient. How many reductions? 2. This box is capable of doing more than 2 reduction ratios, obviously. Now, integral gear motor versus C-face. How do we mount the motor to the gearbox? The C-face, or DIN flange in Europe, is where the motor is made in a standard fashion with a standard shaft, and we have to use some sort of coupling to input it to the gearbox. There are also manufacturers who make integral gear motors where the output shaft of the gear of the motor has the first gear on it and may even have it machined into the shaft. This is very advantageous from a standpoint of space and cost, but causes fits in terms of the world of the end user. Because when that gear motor fails, it fails as a unit. You can't replace the motor versus the gearbox. The ability to replace the motor or the gear separately is very important from the economics of the end user. A motor will typically fail more often than a gearbox. But it doesn't matter. If one fails versus the other, if you use C-face or DIN flange, you can replace that. You can also these are readily available. If you're into an integral gear motor, it's typically that motor or nothing because it's custom. There are no industry standards that define these. And you're typically going to replace the whole thing, so your cost is going to be more expensive. And again, it's a battle between short-term and long-term costs of ownership. One of the interesting innovations that has come out is the use of non-metallic material in the drivetrain. This is a bushing. It's developed by Cone. It was patented. And it's used as sort of a motor shaft condom. I hate to use that kind of term this early in the morning, but that's really what it is. You put it over the motor shaft and you insert it into the hollow point of the gearbox, and that's how you drive the gearbox. This material here is a high density polymer. It doesn't compress. It keeps the motor shaft from metal to metal contact against the inside of the gear input. In reversing applications, it's extremely important because metal to metal on a reversing application will eventually fret and weld together, and then you'll play hell getting that motor out of that gearbox. With the blue bushing, no matter how hard and how long this gearbox runs in high reversing duty applications, you take the 4 bolts off the face, the motor comes apart. It electrically isolates the motor shaft from the gearbox also. And that has some implications when you use VFDs. Now, we are going to have, we're kind of limited. I may continue this class after the holiday, but I'm going to show you these 2 videos on epicycloidal. They are in the the links are in the file that I sent you. So Beethoven. This is an epicycloidal. The input shaft turns here, turns an ellipse that causes the lobes to move along these stiff rods, and you get a reduction ratio in the opposite direction. Note the orange section is moving opposite to the yellow section, which is your input shaft, and it's moving slower. There's a fascinating principle here. We don't have a lot of time, so we can't listen to Beethoven anymore. This is a harmonic drive application. Again, I encourage you to watch these videos a couple times to kind of get. Whoa, sorry about that. Advertising. Now, in the epicycloidal, as you remember, this ellipse was the yellow section driven by the input shaft. Same in the harmonic drive. Radially compliant. It means that it distorts along the radius axis. And that's the principle behind strain wave gearing. It also means that compliance is not stiffness, it's the opposite. So harmonic gearing, in terms of precision gearing, is not as stiff as epicycloidal gearing. It's a very important point to note. Is this zero backlash? Looks like teeth to me with gaps. But no, it is zero backlash because there's always a tooth in contact because of the flexing of that flexible element, as opposed to a normal non-flexing gear where you would have backlash. This is true zero backlash. Okay, so that is those are the two videos that we're talking about here. We're going to run out of time. I'll keep on going for those of you that can stay with me. But applications to establish proper procedure in sizing. These two applications that I've put into this presentation are examples. They can be, the procedure is applied to other types of applications. Again, like I said, good data. Got to get good data. If you ask the customer the question, how accurate does this gearbox need to be? You need a number. It needs to be in arc seconds. Or if he gives you the actual accuracy of his linear move, then you have to translate that back to arc seconds on the output shaft of the gearbox, which is pretty easy to do based on, you know, whatever the gearbox is driving. If he says, I need it really accurate, then your response should be, well, then it's going to be really expensive. How expensive? Well, I don't know. You have to tell me how accurate. That's kind of how that conversation goes. You want a size based on, I really need it. I need high accuracy. There's no number there you can't size. Please, in these discussions, get to the number. And then you can do a good job of engineering your system. If the man says, how much backlash do you need? None. Then you ask the next question. Are you comfortable with the fact that the gearbox will cost 5 times as much as if you can accommodate some backlash? And typically you're going to get the customer to think a little bit. These conversations are very important to have. How you deal with your customer and get to the number is up to you. That's your style in terms of communicating human to human, but get to the number. Now, do not ever copy an application that you're trying to replace based on the existing gearbox data, because it may not have been sized right in the first place, especially if the doggone thing's failing and you're getting an opportunity to replace it, or you're being asked by your boss to replace it. Do you really want to adopt the mistakes of the original unit? The other thing is the original unit may be vastly oversized. Do the engineering. Okay. This is sort of basic stuff. I'll just put it in there for a reminder. When you want us to take a look at stuff for you, and almost everybody at Western Automation has vast experience in doing this, so we can be a resource for you. We also have, in the lines that we represent, a vast army of applications engineers and very experienced people at the factory level. We want to help. We need good data to help. Photographs are really important. You can't take enough photographs and videos in terms of what you want us to do. And this is more just me preaching. So let's get down to, since we have limited time, please read through it. RMS versus peak. RMS stands for root mean squared. It's another fancy word for average. In the application, as I alluded to earlier, average is great for sizing applications that are very slow to accel and continuously run. But a lot of applications in precision motion control are limited by peak torque requirements in the application. And the difference between RMS and peak is significant. We have I'll leave you to read this on your own. Remember I said the target shaft. The target shaft is the output, so you size from the load. And then you work backwards. You don't size from the motor and work forwards. Now, a simple conveyor application. Here we've got a motor, we've got a reduction ratio on a belt drive, or sorry, if we have a motor, we have a gearbox, then we have a belt drive. This is that continuous duty application that I was talking about. And this is the stuff you're going to need to identify. Here's your list. Fill this list in. We can size anything. Notice this is a very complete list. Okay? Windage, do we deal with that much? Not really. But in overland conveyors, it's very important. Breakaway. This is the one that I hardly ever get a definition on. But when you start to push a car, your effort is much greater until you get the car rolling. That is the difference between static friction and dynamic friction, especially when there's ball bearings involved. It's a big difference. So the breakaway torque is going to require power from the motor. If you don't have it, you don't get past that point to get to the rolling inertia, rolling friction. Torque breakaway, torque axle, just talked about that. By the way, on worm gearing, it's really important because in addition to all the other static friction in the drivetrain, you've got higher static friction on a worm gear versus dynamic friction once the worm gear teeth start sliding on each other. Friction is always important in these applications. We make certain assumptions for bearings in terms of the gearbox and the sprockets, etc. But if you're dragging a load across sandpaper, we need to know that. So by the time you get done, I'm going to speed through this because you can review this on your own, and I am time limited here. All of these have been defined for you. That list, I go into detail. Service factor, let's talk a little bit about that. Once you get your number, service factor allows you to add some safety. It's also called safety factor. And in high shock loading applications or where there's a degree of uncertainty in terms of the customer data, because the customer wasn't able to define things accurately, or he's not really sure how the end user is going to use the machine, you add service factor. This is your safety. This is your cover your ass. Fudge factor, a whole bunch of different terms for it. In heavy duty applications, I'll add between 1.5 and 2.0 on the gearbox. I want it to survive. Obviously, it affects economics of the parts selected. In continuous duty applications, I almost never use 1.0 unless I'm at a size of the gearbox that I know is above the requirement, because gearboxes don't have infinite sizing resolution. So maybe I'm already 20% higher than what the requirement is. Well, I've got that service factor built in. Service factor is very important. It's the final multiplier on all of your calculations. Okay, I want to talk a little bit about environmental factors because these are very important. Ambient temperature sources next to a gearbox. Man, how many times have I been blindsided by that? Oh, you forgot to tell me it's running inside a furnace. The thermal on a gearbox can fail the gearbox as much as shock loading, as much as wearing the teeth, as much as bad lubrication. And in many cases, it is more often the cause for failure. It's obviously affected by the efficiency of the gearbox itself. And then all of your washdown characteristics. You guys know how to do that. I don't have to preach on that. But there's one thing I do want to point out. A gearbox is a cavity by definition. It's got gears in it and oil. It's also got air. Air contains moisture, even in the desert. And if you get condensation, well, what does water in your oil do for your hydraulic system? Not good. What about water in your oil in your expensive car? Again, not good. Same thing here. You gotta watch out, especially in washdown applications where you have high humidity, therefore your danger of condensation is even worse. And if you don't design your seals properly, you get weeping going the other way when you hit the output shaft seals with 100 psi of corrosive water. So now that ends the discussion on the continuous duty conveyor application. This is an azimuth and L application, and I chose this one because it's kind of funny, but it's an azimuth and elevation. This lamp rotates, and then the lampshade itself arcs, which is your elevation application. This is just like any other antenna or gimbal that you're going to run into. It can also be used as an example for certain robotic applications. This lamp happens to be going into the Disney parade, so I had some data on it. There's your elevation application. I'm basically driving an arc because the elevation is not 360. So this is very, very common to use sections of gears as opposed to full gears. But here's the definition of the elevation application. Here's the definition of the azimuth or rotate application. Again, driven shaft, output shaft. This is the other data that I had to obtain to do this sizing. Now, this is an entertainment application. I'm dealing with an artist here. The first derivative of position has no meaning to this person. This person is trying to make this do stuff that wows children in a parade. And that's what he's really good at. This is a great example of what I talked about before, communication with the customer. Everything we've gone through here in this session is very definable to us as engineers. We know we need numbers. As a final discussion here, I mean, it took forever to get this data to size this thing properly because the customer wasn't focused on that. And we were successful. Actually, believe it or not, we were called in once this was designed. We actually redesigned it because it didn't work the first time. And that's because the original quote unquote engineer who did it didn't get his numbers. Went with things like, well, I need it really accurate and it needs to go, it's not supposed to go so fast. Those are not numbers. Okay. Read through this because this tells you exactly the conversation that I had with this customer in getting to the numbers. I've gone way over, but I did send you this application, this PowerPoint in the email, so please review it if you have interest. I'm sorry that I had to try to condense this down to an hour, but I didn't do a very good job of it because it's 8:09. And it's time to go to work. I wish you a happy Thanksgiving, and we will see you on December 2nd. I'll publish the subject. But in the meantime, have a great holiday, and thank you very much.
Same to you.
Thank
Thank you.
you. Thank you, Pierce.
Thank you, Pierce.
Yeah.
Enjoy your Thanksgiving.
Thank you.
Thank
you
you,
too.
Pierce.